the University of Michigan. He will talk about long-time existence of steep waterways.
Okay, thank you. So I'd like to thank the organizers for the invitation. So what I'm going to talk about is this work, which was done like at the beginning of the pandemic. So if you have heard it, I apologize for this. Okay, so I guess we have heard several talks on the gravity water wave equation. So I just repeat the model. So the model we are going to study is like the wave in the ocean, right? So we assume that we will neglect surface tension. So we assume the surface tension 0, and we also assume the fluid is inviscid, incompressible, and irrotational, and we will keep the density, the gravity, and we also neglect the air. So assume the air density is 0. Okay, so the domain, so this is a free boundary problem, and the domain is moving, so depend on time. And the fluid is described by the incompressible Euler equation, and V is velocity, and P is pressure, and the right-hand side is gravity, and this is incompressible, irrotational, and the pressure is 0 on the interface, because it's we neglect the surface tension. Okay. And so the last statement says that fluid particle on the interface remain on the interface. Okay, so there's an important condition related to this problem, which is the so-called Taylor-Side condition. Basically, it says that, so this n is the normal, outward normal to the fluid domain. So in other words, this condition requires that the pressure should be increasing in the inward direction. And of course, if you think if this sign is reversed, and then there's a force rip open the fluid, so the bubble will form, and will be the so-called Taylor instability. Okay, so this condition was formulated first by G.I. Taylor in 1949 about a flat interface, and of course there were many work in between. Taylor and in the late in the 90s. So I think this general form has been, well, I find it in the work of Tom Bill, Tom Paul Loenger, okay, and where they formulate this in a general way. Okay, so there's also a strong Taylor-Side condition which says that in fact instead of greater than equal to 0, it should be greater than equal to a positive constant. Okay, so this problem has a long history. So here I have no intention to put on all the work because there's a lot of work in water waves. So this is just some very limited number of work, and it's by no means complete. Okay, so just in my opinion, these are relevant to what I'm going to talk about. Okay, so here is some first work on the local well posedness in sublative space was given by Nalimov for 2D water wave. So he basically shows that if the data is small in sublative spaces, then you can solve it for a short period of time. Yoshihara and Watergrave extend this work to the case where the water wave is finite depths, but with the bottom not intersecting with the fluid interface. And in all these work, that the data are small. Okay. So in this work, we actually show that the Taylor-Side condition always holds as long as, so we are talking about the water wave equation with infinite depths, and as long as there's no surface tension. Okay. And then as a consequence, we can show that for arbitrary data in sublative spaces, you can solve this equation for a short period of time. Okay. So this data can also overturn, and so as long as it doesn't self-intersect, which is, if it self-intersects, then the nature of the problem will change. Okay, so, and this work has been extended into many directions. For example, you can add a surface tension, and you can also deal with a bottom, as long as it doesn't intersect with the interface, and you can also have non-zero vorticity. But in all these cases, you need to assume that the Taylor-Side condition holds, because in all these cases, the Taylor sign condition doesn't hold automatically. So as long as the Taylor sign condition holds, then you can solve the equation for a short period of time, okay, in sovereign spaces. And we also have seen work on for small, smooth, sufficiently localized initial data. Okay, so in this work these early work we were able to show that for data of size epsilon, you can solve the 2D water wave for time exponential e to the 1 over epsilon. Okay, so this is so-called almost global. And for 3D, the result holds for the solution exists for global in time. Okay, for small data. And Germain, Masmoudi, Chattah gave a different proof for global well-postedness for 3D, and additionally, they also obtained the scalability. Okay. And in the work of Ionescu, Pusateri, Alazar, Delors, they were able to extend the 2D result to global using modified scattering. Okay. So, and in this work, they lower the regularity threshold. So Daniel just talked about it. Okay. In the last talk. So the main idea in all this work is that to use the fact that there's no three-way resonant interaction. So basically that says there are two main components. So after a suitable change of coordinates and variables, the water wave equation has no quadratic nonlinear terms. So we know that if we have a nonlinear equation, if there is a quadratic nonlinear term, and if you have local well-postedness, and then if data is of size epsilon, then you can expect to solve it for time 1 over epsilon, right? But if there's no quadratic nonlinear term, then you can solve for time 1 over epsilon squared, okay? But now if we further use this dispersive decay property of sufficiently localized solution, then we can get extended lifespan. So for the 2D water wave, and this is the e to the 1 over epsilon. And for 3D, this is because the decay rate for 2D is 1 over square root t. For 3D, the decay rate is faster, it's 1 over t, so you can get global in time. Okay. But in order to, as I said, in order to get to global for 2D water wave, you have to use modified scaling. Okay. And okay, so a natural question is, can we further remove cubic nonlinearity in the gravity water wave using some kind of normal form change? Okay. And we already were able to see there's no quadratic nonlinear term after some change of variables. Okay, so this problem has been looked at a while ago from a different point of view by Zakharov and Dyachenko. Okay, so Dyachenko and Zakharov show that, well, in this work, by some formal calculation, they show that water wave equation has no three-wave interactions, and all four-wave interaction coefficient vanish on the non-trivial resonant manifold. Okay, and now in this work of Craig and his collaborators, they try to regularize the work of Dyachenko and Zakharov and to show that they wanted to show that for data of size epsilon, the solution exists for time epsilon to the -3. Okay, so they studied a mapping property, but it's in the work of Berti, Fiola, and Pusateri, and they were actually make the work of Dyachenko and Zakharov rigorous, and they rigorous show that for data size epsilon, you can solve the equation for time epsilon to the -3. And this is for periodic data. So in other words, here they are not using any dispersive property. Okay, so what does it mean by, so precisely what did Dyachenko and Zakharov did in their work is that they show there's no three-wave resonant interactions, and now they can write the Hamiltonian after some Birkhoff normal form procedure. The Hamiltonian will look and do a Taylor expansion about the wave height, and has quadratic term, and this is the quintic terms. Okay, no, it's quartic terms. Okay. And what they showed is there's two types of four-wave resonant interaction. Okay, so in fact, the trivial ones are there. So there's no cancellation for the trivial interactions, but there's also the non-trivial ones are all of Benjamin Fair resonances. And what they find is there's the coefficient of H4 vanish on the Benjamin Fair resonances. Okay, so but there's no cancellation for the trivial ones. Okay, so in this work, so basically they constructed rigorously using conjugating pseudo differential flows. Okay, bounded invertible Birkhoff normal forms. Okay, and constructions not explicit. Okay, so this is okay, so the natural question is, okay, so in all these work, the calculation actually was carried out in the Fourier side, okay? So a natural question is, we know the water wave equation is really written explicitly in the physical space. So whether we can see what's really going on in the physical space, okay? So like, explicitly and explicit, we wanted to see explicitly in the physical space, what does this no non-trivial resonant, four-wave resonant interaction means in the physical space, okay? Okay, so now let's just go back to how do we solve the water wave equation, okay? So earlier on, we have seen the talk of Thomas Al-Azhar, okay, and he really studied the Dirichlet-Neumann operator, right, and using pseudo-differential calculus. So here I'm just going to go over a different method of doing this, okay? Not so to study the water wave equation. So here we are going to describe this approach we have been using in all our work, okay? So basic idea is just to reduce the equation on the interface and study the interface. Because the water wave equation, it's a free boundary problem, right? So we want to fix the boundary if we just really look at the equation on the interface. And the reason is, if we look at incompressible irrotational, the potential flow, so the velocity satisfies the Laplace equation. So if we know the velocity on the interface, we can recover it by solving a Dirichlet boundary value problem. Okay, so here, I will just focus on the 2D case, and we are going to use the Riemann mapping or conformal mapping value. Okay, so so let's just write down the equation in Lagrangian coordinates. Okay, so we always in 2 dimensions we always identify a point with a complex variable x plus iy, and we can write a free surface in like z equal to z alpha t. Alpha is a Lagrangian coordinate. That means that z alpha t indicate the particle trajectory of the same particle on the interface. Okay, so if we take derivative to time, so this little t dt means time derivative, we get velocity, and if we take 2 derivative to t, we get acceleration. Okay, and we also write the gravity, just minus I, we normalize it to be 1. So minus I. And we know the pressure is 0 on the interface, so the gradient P should point in the normal direction. Okay, so we just do decomposition in the tangent normal direction, and only the normal direction survives, and we just write like this. Okay, so because this interface taking derivative to alpha is a tangent vector, and multiply I gives you a normal vector. So this is a normal vector. A is just, you write down A is just negative dpdn times the 1 over the length of the alpha, okay, because n is a unit normal vector. And now, so incompressible divergence curl equal to 0 of the velocity precisely correspond to the fact that V bar is holomorphic, okay. So this means that Zt bar, that's V bar, that's a boundary value of the holomorphic function. Okay, so now we just go back to this Euler equation, the free boundary, the water wave equation, right? So this left-hand side is acceleration. So acceleration is really just ztt, right? So the 2-time derivative to the particle trajectory on the interface. And then this gravity just moved to the left-hand side becomes positive I, and negative gradient P is just IA Z alpha. Okay, and divergence curl equal to 0 is that this, because it's a V bar is holomorphic, it satisfies a Cauchy integral formula. So this H is there's a principal value. Okay, so the principal value twice of the Cauchy integral. Right? So you just write down the Cauchy integral, and that's the equation it has to satisfy. Okay, so if we look at this equation, it's not easy to understand what's going on, right? Because 1 over Z alpha minus 1 over Z beta is unknown. Okay, so we have unknown in the denominator. It's just too nonlinear, too complicated to understand. And this is where the Riemann mapping or the conformal mapping becomes useful, or at least very helpful to understand the structure of the equation. Okay, so we look at the Riemann mapping from the lower half plane. So this is lower half plane to the fluid domain. Okay, so this is how it looks. So this is P minus is here, okay, and this Riemann mapping say going to here. Okay, so this is omega t, and we know that the conformal mapping also has a property that takes a point on the boundary to a point on the boundary. Okay, so then naturally psi of alpha prime t exactly give us an equation for the interface, and we call it Z alpha. And that's the first one. Okay, so this precisely describes the interface. And of course, between the Riemann mapping variable and also the Lagrangian coordinates, there's a change of variable. Remember, alpha is the Lagrangian coordinates, alpha prime. So there's a change of variable. We just use H to describe this change of variable. Okay, and this is just a notation. Okay, and now if we take, so this is again a notation. Capital DT is a material derivative. In other words, this is really the derivative, time derivative with respect to following the particle trajectory. Okay, so the material derivative, there's a change of, this is basically the chain rule, right? So there is a B come out. Okay, capital DT is DT plus dB alpha. Okay, and this will be the velocity. And if you take one more material derivative of the velocity, you get acceleration. Okay, and these are just notation. So now we just rewrite the interface equation in the Euler equation in terms of the Riemann mapping coordinate alpha prime. Okay, so it's the same as before, right? So because remember this is acceleration, so it's just a notation, acceleration, and this is the negative of the gravity. Now right hand side is supposed to be IA Z alpha, right? So basically it should be a quantity points in the normal direction. But if I look, so this A1 is a real value function. So if you just look at I divide by 1 over Z alpha bar is same points in same direction as I times Z alpha. Yes. Okay. Okay, so this is, so we can just write down the Euler equation on the interface this way. And so the advantage of using the conformal mapping is that the equation for the on the interface for the velocity becomes much simpler, right? Because this time that if anything holomorphic in the low half plane is satisfied Z I minus the Hilbert transform equal to 0, this Hilbert transform is just simply like this. Okay, so it's just like this. Okay, and this is something very simple, easy to understand. Okay, so now this makes the equation easy to understand, and also 1 over Z alpha. So remember, Z alpha is the conformal mapping, right, on the interface. If you take derivative to alpha, you really just get the Jacobian of the Riemann mapping. So this is like Jacobian of the Riemann mapping, of course, is holomorphic, and here we subtract 1 because we assume that the conformal mapping tends to 1 at infinity, and this equation only holds for quantities that decays at infinity. So you subtract 1, this is also what, and with these two conditions, you can derive a formula for A1. Okay, so this has been done a long time ago in this first work in 97. So we have this formula. Okay, so this is exactly the formula we use to show that the Taylor sum condition always holds. So in fact, this quantity A1 equals to this formula. Okay, so and the second quantity here is always greater than or equal to 0, non-negative. Okay, this is by just integration by parts. Okay, you can see that this is a non-negative quantity. So A1 is always greater than or equal to 1. So A1 greater than or equal to 1, and remember, if we follow the notation carefully, and negative dpdn times the length of Z alpha is exactly equal to A1. So A1 greater than or equal to 1, this, in other words, shows negative dpdn has to be greater than or equal to 0, right? Because the left-hand side, the length is always a non-negative quantity. Okay, so this is how we prove that the Taylor sum condition always holds. So the good thing is we have a precise formula for A1, and we also have a precise formula for B, which is written like the real part of I minus H is Zt divided by Z alpha. Okay, so this Zt is the velocity. Okay. Okay, so with all these formulas, but there is a problem with this formula. So far, this whole thing is completely fully nonlinear. So it turns out just by taking one time derivative, material derivative to the first equation to the boundary equation. Okay, so just take one material derivative, one time derivative to this equation, we get a quasi-linear equation. So if we take one derivative to this, we get ztt, right? So the right-hand side has two terms, I zt alpha times A and plus I ATZ alpha. Okay, so now we moved one of the terms on the right-hand side to the left, and we also put a bar there. Okay, so the reason I'm writing is this way is that we can show the left-hand side is the higher order term, the right-hand side is the lower order term. And there's a simple explanation why the right-hand side has to be lower order. Okay, so this is because that, if we look at Zt bar as a holomorphic, so taking derivative and write also dt twice and also IA d alpha make it almost holomorphic. Okay, so it's not that holomorphic, but close to being holomorphic. But the right-hand side, A is real valued. So AT, and then if we neglect bar, so the right-hand side is really just pointing in the normal direction. Okay, and the boundary value of holomorphic, of a holomorphic function, if the tangential direction equal to 0, the normal direction also have to be 0. Okay, but being almost holomorphic means that this is this is why this not really close to being 0, but this is lower order term. Okay, so in fact we have a precise formula for this, but I'm just not showing it here. Okay, so this is a lower order term, but this is also quadratic. Okay, and this is also a low order term because here has only 2 material derivatives, and here we have 3 derivatives. Okay. Okay, so now in Riemann mapping variable, this reads like this. Okay, so now maybe let me just sidetrack a little bit. So where is the Dirichlet to Neumann operator where Thomas has been talking about? So the Dirichlet to Neumann operator in the Riemann mapping variable exactly is I d alpha here. Okay, so now this is why we find that using conformal mapping easier in some case. It's because this operator we can understand. It's easier to understand, right? Because it's I d alpha. Okay, so precisely what this is. So if we have a function which f is holomorphic, so if f is holomorphic, then this means that f equal to the Hilbert transform of f itself, right? So if I compute I d alpha and hf, so plug in hf, but this, remember this h in my notation has I in the denominator. Okay, so this is like a little bit different from the the ones you typically see in harmonic lattice. So this gives us exactly the first order derivative. Okay, I should really just write it's d alpha. Okay, so absolute value of d alpha. So this is the duration to none. Okay, so now of course, so here, so the left hand side is like dt squared plus a non-negative operator with a, because we have shown that a1 is greater than or equal to 1, right? So this is a coefficient, non-negative coefficient. So this looks like a wave type operator, okay, wave type, and the right hand side is lower order term. So we can use energy estimates and then the usual methods for hyperbolic type of equation to prove the local well posedness. Okay. So here the typical equation in water wave. So here this is the equation acting on the velocity, right? So this is a typical operator acting on the velocity equal to something quadratic in the lower order term. Okay. So if you want to act instead on 1 over z alpha, you will get a similar equation as well. So this is how typical terms look like, the equation looks like. Okay, so now what is the normal form so let's recall what's the normal form transformation we found in this work. Okay, so now if I take the velocity potential, and now if I realize it on look at the trace of the velocity potential on the interface. Okay, so it turns out that if we just look at this quantity I minus h of the velocity potential acting on. So in other words, you look at the projection of the velocity potential in the space of holomorphic function in the air region, okay? And you also look at this z minus z bar. So z minus z bar has no real part, right? So you look at the height of the interface and you project it to the space of holomorphic function in the air region. And both of these quantities satisfy equation of this type, okay? So the right-hand side, the quadratic nonlinear term is completely removed. Okay, so it's just cubic and something explicit you can write down explicitly. And the left-hand side, this a is negative, something related to negative ddtEj. So it still has quadratic nonlinear term. Now it turns out a change of coordinates given like this, so it's twice of the real part of the interface. It's like 2x minus h. H is the change of variable from the Lagrangian to the Riemann conformal mapping coordinates. Okay, and if you do this change of coordinates, and then this will completely remove the quadratic nonlinear term on the left hand side. So the equation will look like this: dt squared minus I d alpha. So this is like look like linear constant coefficient. Okay, so but of course there is still something nonlinear involved here, but I mean, if straightforward speaking, it looks like this. Acting on this lambda after change of coordinate becomes cubic, and this acting on this is cubic. Okay. Now with the quadratic nonlinear term completely removed like this, then we can just so we can do the usual thing, right? So we just construct the basic energy functional as the following. So this basic energy functional is for this equation. Okay, so this like dt squared minus IA d alpha. Okay, so we moved 1 over a to here. So we can just plug in not only lambda and pi, we can also plug in all the derivative of these quantities, and then we take ddt, right? So we will have all the derivatives of these quantities satisfy ddt of this energy functional acting on this is quartic. Okay, so of course if I just look at derivatives in the spatial variable or time variable, then I will get existence of solution for time of order epsilon to the -2 for data of size epsilon. Okay, so this means if I do not involve anything dispersive. But of course with the equation with no quadratic nonlinear term, you can also use method of vector fields. So if you replace this derivative by vector fields, then you will get decay, right? So then using the decay, we can show that the solution exists for time to almost globally. And now this similar quartic estimate also plays key roles in this work of Ionescu Pisoteri and Alazardalo, Hunter, Ifrin, Tataru. Okay. But what's important, what's new in significantly in this work is that they use modified scaling to get to global. Okay, so far all involved is just that the fact that basic fact there's no three-way interactions. Okay, so we can remove the quadratic nonlinear. Okay, so a natural question is, well, if this is so useful, can we actually construct a sequence of energy functionals so that ddt of this equal to quintic? Okay, so just like say, so if we can make it quintic, then supposedly the cubic nonlinearity is also removed, right? So how do we do this? So of course, I mean, naively you want to just look at this, right? So because this is something precisely there, and you look at it, and then you move it to the left-hand side. Try to move it to the left-hand side. But if you start to do this, there is some basic fact we have to keep in mind. Because anything you want to find antiderivative with have to have some symmetry. Because if you have anything quantic, so if you take a derivative, you will have derivative hit on the first term, and then it also hit on the second term, right? And also it hits on the third term. So in other words, only when these four terms present simultaneously, we can just create one term like this. Okay, just but unfortunately with this form, nothing is. It's quite messy on the right-hand side. So we have to redo all the work, okay, and to make things symmetric, okay, because these right-hand side look very symmetric. So we want to make things symmetric. Okay, so we have to reconsider what we have done before. Okay, so we have to re-understand the earlier work and try to see to keep in mind things need to be symmetric. Okay, so here we just start with this quantity. Okay, so this quantity, this again, remember here we find that the projection of the velocity potential to the space of a holomorphic function in the air region is nice. Okay, so we start again just, and also remember that in the conformal mapping variable, things are easier to understand. So we just rethinking everything in the conformal mapping variable, okay, and this is the velocity potential, and we project to the space of holomorphic function. So in fact, so being flat and being holomorphic in the air region, you just put a bar, right? Because H is purely imaginary, okay? So it doesn't make any difference, you just project to the space of holomorphic functions, I plus H, okay? If you want anti-holomorphic, you just put a bar on top of it. So it turns out, I just say what have worked, okay? So instead of this, you remember this is the main operator we have been dealing with. But instead of this one, so it looks like that this one works better when we want to deal with things symmetrically. So this is a material derivative, but instead of material derivative, twice of material derivative, every time you take material derivative, you take projection and then you take material derivative. Okay? And this one is, remember this, it used to be A1, but actually only the gravity term survived, 1 over the alpha square. So this A1 has two terms. Right, this term disappeared. Okay. This one disappeared and only gravity survived. Okay. So this operator acting on this turns out equal to something purely anti-holomorphic, right? So Q is holomorphic, the right-hand side is anti-holomorphic. And it's also quadratic because zt is imaginary. So here, when we talk about quadratic cubic, we think things are small, right? So velocity is small, 1 minus 1 over the alpha is also small. So right-hand side is quadratic, but anti-holomorphic, and this is holomorphic. So this automatically already give us a further cancellation, right? Because the anti-holomorphic thing cannot equal to holomorphic. So unless both are 0. But of course, the left-hand side is, after acting by an operator, it does have anti-holomorphic residual there, so which is cubic. Okay, so now it also turns out that instead of, so this will be the beginning point, right? So, and we want to construct a sequence. So this sequence is every time you take a material derivative, you project. So you keep repeating this process. And this sequence will satisfy this equation. So I'm going to show you what is the right-hand side. So this right-hand side is cubic with some nice symmetric structure. Remember, we want things symmetric. Okay, so the first one is 0 because this is purely anti-holomorphic. Okay, and again, also that we find this symmetric form of energy functional is more useful than the one I have written previously. So it's like, if you have two holomorphic quantity, you look at ID alpha, the theta 2, and then the material derivative and the projection of the theta 1, and this, look, they are symmetric. So if you take derivative to this energy functional, this is a general theorem, right? So this equal to this. So this is where this operator comes in. Okay, so this is why we are dealing with this operator, because it, after taking derivative equal to this. Okay, so now this is the sequence we construct. Okay, so now we take derivative of this, and using this energy identity, we find this equal to that. Okay, so now there is also a formula, recursive formula for of this quantity, and this satisfies the following. Okay, so this triple form is completely symmetric. In fact, if you use the holomorphicity of the integral or Cauchy integral formula, you can write this integral completely into 4 factors of the same thing, similar things. Okay, so except like 1 over the alpha zt, I 1 over the alpha, and d alpha theta j. So now this is symmetric, but what are the quantity involved? Okay, so this is a quartic in terms of only derivatives of the 1 over the alpha and zt, okay, because it involves only the difference. Okay. So now what is the quantities involved? So with some further, of course, if you keep looking at this equation, you will see that actually 1 over the alpha is something like ztt. So one derivative to zt. Okay. The alpha of theta k is k many derivative to zt. So in other words, we will have a quantity, this is 0 derivative to zt, this is 1 derivative, and this is L derivative, and this is 1 derivative. So we have different orders of time derivative, material derivative to these basic quantities zt. Okay. So now in order to put it in this form, symmetrically we want the derivative to move to the right place, okay, like to evenly distribute out. So we want an energy functional that allows us to move the material derivative from factors to factors. Okay. Now we know that this main operator acting on basic quantities are quadratic. Okay. So it turns out that taking derivative to this quantity give us the right-hand side. So this quintic we are happy with, but here you see that there's an extra material derivative here, and there's an extra material derivative here. So in other words, you can think about the right-hand side as 1 material derivative to q is moved to the 1 material derivative to h bar on the second term after we perform something like this. Okay. So this allows us to move derivatives. So of course, so if we move the derivative evenly, then we can get to this point. So if f to the 4th derivative, it will be 4f derivative f to the power 3, right? So if we can, so in fact, if we even move the derivative evenly, the right-hand side, if only one of the term have active derivative and then just recopy this, we can find antiderivative. So now we just try to move the derivative to make it evenly distributed. So it turns out these are the corrections we need to do. Okay, so just using this function. Okay. And this is some other corrections. And we find that, so we take these energy functional, and after these modification, we find this quantity satisfies something equal to quintic. Okay. And also has some special structure. So this is something explicit. Okay. And we can see that it only controls spatial derivatives of the basic quantity 1 over z alpha and zt. And this means that this energy functional is small even if 1 over z alpha and zt are large. So it's small as long as the derivatives of these quantities are small. Okay. Okay. So waves with large steepness and velocity can be small in this energy functional. And ddT of these energy functional is quintic, and that's also in terms of quantities involving only spatial derivatives of 1 over z alpha and zt. Okay. So now, so I am just going to present you one analytic result. So in fact, I think this is the main result of the work. Okay, but this is one possible applications of this result. Okay, so here the scaling law for the water wave is the following. So these are the scaling invariant norms. Okay, so this is 1 over z alpha minus 1 h dot 1/2 norm, and zt alpha L2 norm, and 1 over z alpha minus L infinity. So this is something involves the steepness of the water wave. Okay, so of course the steepness should be scaling invariant. So we look at this quantity. Okay, so this quantity involves the first line is scaling invariant, and the second quantity exactly is one derivative of these scaling invariant quantities. Okay, so now we assume that the initial data is smooth enough. Now there is epsilon sufficiently small so that if L0 is sufficiently small, like less than epsilon, and if this is less than 1, it doesn't have to be small, as long as it's less than 1. Okay. So the steepness doesn't have to be small. Okay. And E1 times E3 is less than some universal constant. So this is a scaling invariant quantity as well. So E1, E3 are in the energy sequence I constructed. Then so for data of size epsilon, the lifespans is at least of order epsilon to the minus 3. So here, for this result, we do not assume anything that's, we are not using anything dispersive. In other words, we can, so here I'm writing the result in terms of the whole line, but it also holds for this periodic case. So same construction also holds for the periodic case with some modifications with some constants. Okay, so now if we assume only the scaling invariant quantity is less than epsilon, and these two quantities are bounded but not necessarily small, then we sacrifice the time a little bit by, so the time of existence is epsilon to the minus 5 over 3. Okay. Okay. So what is the main idea? So what is this E1 is E3? So if we look at the construction of the energy function, we find all our EIs, EJs really control these homogeneous norms, right? So E1 precisely controls the L2 norm of this quantity and the H dot 1/2 norm of this quantity. E3 controls exactly one spatial derivative above these two. So you multiply these two, you get a scaling invariant quantity. And the reason the product is involved is really just because we want to control this quantity for time of order epsilon to the minus 3. And that's the one way of controlling it, and because we are able to control E1 and E3 for this time of order, so this, and we use this Sobolev embedding. If we can control the right-hand side for this time of order, we are able to control the left-hand side for this time of order. So if this quantity is strictly less than 1 initially, then we are able to show it remains less than 1 for time of this order by using this Sobolev embedding. Okay. So M0 does not need to be small, and so delta less than 1 can be as close to 1 as possible. Okay, can be close to 0 as possible. So this means that slope can be arbitrarily large. Okay. Now this is like the second part of the theorem is really quite cheap by just doing something rescale the initial data. Because if we rescale the data, we find this extra derivative give us epsilon in front of the norm. Okay. So the rescale, the solution will have lifespan epsilon to the -3 by applying the first part, and then going back to the original one, you get lifespan epsilon to -5/3. Okay. So this inequality, this quantity to be strictly less than 1 means that we are only dealing with graph. Okay. Okay, so the main idea of proof is just using this quintic vanish sequence, because this epsilon j control these homogeneous Sobolev norms. Okay. DDT is of order epsilon to the 5. Okay. And we actually only use j between 2 and 4. Okay. And DDT of this is also satisfy this, provided the system. Okay. So this is how we prove the result. Okay. So of course, I mean, after this work, we also tried some to look at different types of free boundary problems, and we find that similar calculation applies to a variety of similar free boundary problems. And for some problem, it also has higher order integrabilities. Okay. And I'd like to mention this recent work of Dyachenko Zakharov, and they also proved quartic integrability using a different method. And also they have a long time existence, I think, to the epsilon to the -6, I just checked, by further using the so-called Zeno-Strickhouse estimate. Okay, so by further using dispersive property, and then they can push the existence for a little longer. But if without using dispersion, they also get epsilon -3. So, thank you.
Can you plot, please, the graph of a possible solution with initially velocity 0 and a graph whose slope would be large, for which your inequality applies?